Hello there, and welcome to the Serene Scroll. I'm so glad you're here. Maybe it's been a long day, a long week, and you are seeking a quiet space to simply let go. Find a comfortable position now, allowing your body to feel heavy and supported. Let the rhythm of your breath begin to slow each exhale, a gentle release of the day's concerns. We are about to embark on a quiet journey, a story woven from the fabric of the cosmos and the threads of human wonder. And just before we begin, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. There is no need to do anything now. Simply rest and let the story unfold. Tonight, our journey begins not with a spaceship, but with a question. It is a question as old as consciousness itself, one that has been whispered around campfires, etched into stone, and debated in the halls of ancient libraries. It is a question that arises naturally, almost inevitably, whenever a human being looks up into the deep velvet darkness of a clear night sky. The question is simple, yet it holds within it the entire scope of our cosmic loneliness and our boundless hope. Are we alone? This question is not a modern invention. It is not the exclusive domain of radio telescopes and complex equations. It is an ancient echo, a fundamental part of the human conversation with the universe. Long before we knew the true nature of the stars, our ancestors felt their pull. They saw in the celestial dance a mirror for their own lives, a world of order, of myth, of distant, untouchable gods. But even then, among the certainty of divine clockwork, a different thought occasionally found purchase, a quiet and radical suggestion. This idea was born from a principle of generosity, a philosophical intuition that a creator or nature itself would not be wasteful. This is sometimes called the principle of plenitude, the belief that the universe is as full of life and existence as it could possibly be. Why would a limitless power create only one small inhabited world in a vast empty theater? It seemed to some thinkers a profound and illogical scarcity. If the conditions for life could exist here, why not elsewhere? This wasn't a scientific theory. It was a feeling, an aesthetic and philosophical preference for abundance over emptiness, for a cosmos teeming with variety rather than a single lonely spectacle. It was the first stirring of the idea that the silence of the night sky might not be emptiness, but simply a distance too great for our ears to cross. In the sun-drenched courtyards of ancient Greece, this idea found its first true champions. Philosophers like Democritus and his follower Epicurus imagined a universe built not from divine will, but from more fundamental indivisible particles they called atoms. They pictured these atoms as infinite in number, tumbling through an endless void. As they collided, swerved, and hooked together, they would form everything we see: rocks, water, plants, people. But if the atoms were infinite, and the void was infinite, then the combinations they could form must also be infinite. It was a staggering, almost dizzying leap of logic. It meant that our world, our Earth, was not a unique creation. It was merely one likely outcome of this cosmic dance of atoms. Somewhere else, far beyond the reach of our eyes, other atoms must have combined in similar ways to form other worlds. And on some of those worlds, they reasoned other living things, perhaps even other thinking beings, must have arisen. Epicurus wrote of infinite worlds, some like ours, some unlike ours, scattered through the endless void. Imagine standing in an ancient Greek portico, the air warm and smelling of salt and olive trees, listening to this idea for the first time. For centuries, the sky was the realm of the gods, a perfect and unchanging tapestry. Now these thinkers were suggesting it was just more space, with more worlds. It demystified the heavens, and in doing so, expanded them beyond imagination. It replaced a single curated divine stage with a sprawling, wild, and uncountably vast cosmos. This was not a popular idea. For most, the prevailing view, championed by giants like Aristotle and later codified by Ptolemy, was far more comforting. It placed the Earth at the very center of everything. Our home was unique, stable, and profoundly special. Around it, the sun, moon, planets, and stars were fixed to a series of perfect crystalline spheres, turning in a harmonious, predictable celestial ballet. This geocentric model was elegant, intuitive, and deeply flattering to humanity's sense of importance. It reigned for over 1,000 years, a beautiful and intricate cage for the human imagination. The universe had a clear center, a clear boundary, and a clear purpose that revolved around us. The question, "Are we alone?" was meaningless. Of course we were. We were the sole beneficiaries of a tailor-made cosmos. The stars were not other suns. They were merely lights affixed to the outermost sphere for our benefit and admiration. The whispers of infinite worlds faded, becoming a footnote in the history of a few fringe thinkers. The cosmos felt known, mapped, and comfortably small. For centuries, this comforting picture held. The celestial spheres turned, the planets wandered in their prescribed paths, and humanity slept soundly, believing itself to be at the heart of all creation. But a quiet tremor was beginning to shake this foundation. It came not from a philosopher's argument, but from the meticulous columns of numbers in a Polish astronomer's notebook. Nicholas Copernicus, a canon in a quiet cathedral town, spent decades observing the heavens. The math of the Earth-centered model was becoming impossibly complicated. To explain the strange retrograde motions of planets like Mars, astronomers had to invent elaborate epicycles, wheels turning upon wheels, a series of clumsy corrections to make reality fit the theory. Copernicus found a much simpler, more elegant solution. What if he proposed the Earth was not the center? What if it, along with the other planets, revolved around the Sun? He knew how radical this idea was. He delayed its publication for years, releasing his masterwork, On the Revolutions of the Celestial Spheres, only on his deathbed in 1543. At first, it was seen as a mere mathematical convenience, a clever trick for simplifying calculations. But the seed of a monumental shift had been planted. We were no longer the stationary audience. We were part of the celestial dance. If Copernicus quietly unlocked the door, it was an Italian astronomer, Galileo Galilei, who threw it open for all to see. In the early 1600s, Galileo pointed a new invention, the telescope, toward the heavens, and what he saw shattered the old world forever. He looked at the moon and saw not a perfect smooth orb, but a world with mountains and valleys, plains and craters. It was imperfect. It was a place much like Earth. He turned his gaze to Jupiter and saw 4 tiny points of light circling at moons. This was definitive proof that not everything in the universe revolved around the Earth. The crystalline spheres, if they existed, were broken. He looked at the Milky Way and saw that its hazy, ethereal light was not a celestial cloud, but a dense, uncountable swarm of individual stars, too distant to be seen with the naked eye. Each of these observations was a chisel blow to the old Earth-centered model. The sky was not a simple, perfect ceiling. It was deep. It was complex. And if the moon was a world, and Jupiter had its own system of worlds, then what were all those other stars Galileo had revealed? The ancient idea of other worlds dormant for so long began to stir once more, this time with the weight of observation behind it. The universe was becoming unimaginably vast, and our own position within it was becoming less and less special. This expanding cosmos was a terrifying prospect for the established order, an institution built upon the bedrock of a unique Earth and a singular human story. And no one embodied the revolutionary and dangerous potential of this new cosmic vision more than a philosopher and former Dominican friar named Giordano Bruno. Bruno was not a careful astronomer like Copernicus or Galileo. He was a visionary, a poet of the infinite. He took the Copernican model and ran with it far beyond the realm of cautious science. He read the ancient atomists and saw a truth that resonated deep within him. If the Earth revolved around the sun, he declared then, the sun was just a star. And if the countless stars in the night sky were other suns, then they too must have planets circling them. And those planets, he passionately argued, must be inhabited. For Bruno, the principle of plenitude was a divine truth. A God of infinite power would create an infinite universe with infinite worlds and infinite expressions of life. He traveled across Europe, a fiery and eloquent preacher of this new gospel. He spoke of a universe with no center and no circumference, a cosmos where every star was a potential home, every world a potential cradle for beings who also looked up at their own skies and wondered. This was not just heresy against religious doctrine. It was a fundamental challenge to the entire structure of human importance. If we were not at the center, if we were just one of countless inhabited worlds, then what became of our special relationship with God? What became of our claim to be the pinnacle of creation? Bruno's ideas were exhilarating to some, but profoundly dangerous to the powers that be. After years of wandering, he was arrested by the Roman Inquisition, imprisoned for years, and interrogated. He refused to recant his vision of an infinite populated universe. In the year 1600, he was burned at the stake in a public square in Rome, condemned as a heretic. His crime was not one of science, but of imagination. He had dared to populate the void. The tragic fate of Giordano Bruno marks a turning point. It shows how deeply the question, "Are we alone?" is tied to our sense of self. To even ask it seriously required a profound act of humility, a willingness to accept that we might not be the sole protagonists of the cosmic story. Bruno's martyrdom did not extinguish the idea. It only highlighted its power. The old universe, the small, comfortable, human-centric cosmos, was dying. A new one, immense, mysterious, and filled with staggering possibility, was being born. The whispers of the cosmos were no longer faint philosophical speculations. They were now being amplified by the lenses of telescopes and the logic of mathematics. The conversation had changed. The question was no longer if other worlds could exist, but rather how many there were, and what they might be like. The philosophical door had been thrown open, revealing a view of reality more vast and awe-inspiring than anyone had ever dared to dream. But what truly lay beyond that door? Just how large was this newly imagined stage, and how many potential points of light might be scattered through its endless darkness? To begin to answer, that we must leave the realm of philosophy and turn our gaze fully to the heavens, attempting to grasp the true mind-bending scale of an ocean of stars. Let us begin our journey, not by looking up, but by looking inward and then outward. Feel the space you occupy right now, the gentle pressure of where your body meets the surface beneath you, the soft weight of the air on your skin. This room, this small, quiet sanctuary, is our starting point. It feels like the entire world for a moment, but now, with a quiet act of imagination, let us begin to pull back. Imagine yourself floating gently upward, rising through the roof, seeing your home, your street, your neighborhood shrink below. The sounds of the world fade into a soft, collective hum. You continue to rise, ascending through the thin, wispy clouds until the grand curve of the earth reveals itself. Below you now is a swirling marble of impossible beauty, deep sapphire oceans and continents of emerald and ochre, all veiled in a delicate milky haze of atmosphere. This is home, our island in the cosmos. For most of human history, this was the entire known universe, a flat plain under a dome of glittering lights. But a quiet revolution in thought began to whisper a new story. It suggested that our world was not the center of everything, but simply a world one among many. This idea, the Copernican principle, is not one of demotion, but of liberation. It frees us from the center of the stage and makes us part of a vast cosmic audience and perhaps part of the cast itself. It whispers that the rules we see here of physics, of chemistry, are likely the same rules that play out everywhere. We are not a special exception. We are a beautiful example. From this vantage point, we see our planet as it truly is a traveler. It is tethered by the invisible force of gravity to a star, our sun. Let's drift further until our solar system lays before us like a grand celestial clockwork. At its heart, the sun burns with a steady, life-giving fire. Around it, the rocky inner worlds dance their ancient orbital waltz: Mercury, Venus, our Earth, and Mars. Further out, the gas giants, Jupiter with its swirling stormy eye, and Saturn adorned with its breathtaking rings of ice and dust. And beyond them, the lonely, icy sentinels of Uranus and Neptune wandering in the cold, distant dark. For centuries, this family of 8 planets was the limit of our imagination for worlds. We saw the stars as mere points of light, fundamentally different from the solid ground beneath our feet. But the Copernican idea invites a bolder question: if our Earth is a planet and it orbits a star, and the night sky is filled with other stars, could it be that those distant lights are also suns? And if they are suns, could they too have families of worlds circling them? To answer that, we must pull back again further than any human has ever traveled. Our entire solar system, with its giant planets and vast distances, shrinks to a single, indistinguishable point of light. We are now drifting in the local neighborhood of our galaxy, the Milky Way. And what we see is staggering. The stars are not scattered randomly. They are gathered into a colossal spinning disk of light, a city of suns. From our new perspective, we see that our sun is just one of 100 billion, perhaps as many as 400 billion stars in this single galaxy. Take a moment to let that number settle. Not a million, a billion. And then multiply that by hundreds. For every single human being who has ever lived there are dozens of stars in our galaxy alone. Some are ancient red giants bloating at the end of their lives. Some are young, fierce blue stars burning hot and fast. And many are like our own, sun-calm, yellow, middle-aged stars, stable enough to warm planets for eons. We live in a spiral arm of this grand structure about 2/3 of the way out from the dense glowing center. We are in the quiet suburbs of a stellar metropolis of unimaginable size. The sheer number transforms the question from if there are other planets to how could there not be, but the journey isn't over. Let us drift even further out. Our magnificent Milky Way, with its hundreds of billions of suns, begins to look like a luminous pinwheel, a splash of cosmic cream against black velvet. And we see it is not alone. Nearby is Andromeda, a sister galaxy, even larger than our own, hurtling toward us for a gentle, slow-motion merger billions of years from now. These two, along with dozens of smaller dwarf galaxies, are all bound together by gravity, forming what we call the local group, a small, quiet cosmic town. And as we continue to pull back, we see that our local group is just one of many. It sits on the fringe of a much larger structure, the Virgo supercluster, a sprawling collection of thousands of galaxies. The universe, we begin to realize, is not empty space with things in it. The galaxies themselves form a structure, a vast luminous web of filaments and nodes stretching across billions of light years. The empty spaces, the great voids, are just as much a part of the pattern. Our cosmic address becomes more profound. We live on Earth in the solar system, in the Orion arm of the Milky Way galaxy, which is part of the local group on the outskirts of the Virgo supercluster. And even this we now know is just one lobe of an even grander structure. We have named Laniakea, a Hawaiian name that means immeasurable heaven. We are a single grain of sand on one beach of an island, in an archipelago, in an ocean that covers a world we have only just begun to map. With this sense of scale, let us now zoom back in, returning to the level of individual stars. For decades, the existence of planets beyond our solar system, exoplanets, was pure theory. We suspected they were there, but we had no way to see them. They are far too small and dim, lost in the brilliant glare of their parent stars. It is like trying to spot a firefly next to a searchlight from miles away. Then, in the early 21st century, we built telescopes of extraordinary sensitivity. Missions like NASA's Kepler Space Telescope were launched not to look at stars, but to stare unblinking at a single patch of them year after year. It was watching for something incredibly subtle, a tiny periodic dip in a star's light. The kind of dip that could only be caused by a planet passing in front of it, an event called a transit. It was a cosmic game of shadows. And what Kepler found, followed by its successor TESS, changed our understanding of the cosmos forever. It found planets, not just a few. It found thousands. It found them everywhere. It found small rocky worlds like Earth and Mars. It found colossal hot Jupiter's gas giants orbiting impossibly close to their stars. It found super-Earth's worlds larger than our own, but smaller than Neptune. It found planets orbiting two suns like Tatooine from science fiction. It found orphan planets wandering alone through the dark cast out from their home systems long ago. The data poured in, and the conclusion was undeniable. Planets are not rare. They are common, utterly, wonderfully, mind-bogglingly common. The current understanding is that on average, there is at least one planet for every star in the sky. Our galaxy is not just an ocean of 400 billion suns. It is an ocean of at least 400 billion planets. The potential stages for life are more numerous than we ever dared to dream. But of course, not all of these stages are suitable for a story to unfold. Many will be too hostile, too chaotic. So astronomers began to narrow the search, looking for worlds that were, in the words of the fairy tale, just right. This led to the concept of the habitable zone, often called the Goldilocks zone. It refers to the orbital region around a star where the temperature is neither too hot nor too cold for liquid water to exist on a planet's surface. Too close to the star, and any water would boil away into space. Too far from it, and the water would be locked up in a permanent global sheet of ice. But in that temperate middle ground, that gentle cosmic shoreline water, the solvent we believe is essential for life as we know it could pool. It could form rivers, lakes, and oceans. Kepler and other surveys have been searching for planets specifically in this zone, and they have found them. Based on the statistical data, astronomers now estimate that there could be as many as 40 billion Earth-sized planets residing in the habitable zones of stars within our Milky Way galaxy alone. Let that number sink in. 40 billion worlds that are roughly the right size and the right temperature to host liquid water. Think of it. As you lie here breathing quietly, you can imagine them. Worlds with skies of a different color, lit by a sun that is redder or paler than our own. Worlds with oceans that stretch from pole to pole. Worlds with continents of a shape we cannot even conceive. 40 billion potential cradles waiting in the silent darkness of the galaxy. We have drawn a map not of destinations we can visit, but of places where a story like ours might have begun. The sheer statistics are overwhelming, shifting the burden of proof. It no longer seems a question of if life exists elsewhere, but where it exists and what form it has taken. We have found the potential homes. The stages are set across an ocean of stars, numbered in the billions. But this discovery, as profound as it is, leads us to a deeper, more fundamental question. When we search for echoes of life in the void, what is it precisely that we are listening for? What is this fragile, tenacious, and mysterious blueprint of being that transformed our own world from a sterile rock into a living, breathing biosphere? Before we can find it, we must first try to understand what it even is. Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet and often hidden corners, has been showing us just how small our imagination has been. To begin, we can start with the recipe. We know the one that has worked so brilliantly for billions of years on this world. It seems to require three fundamental ingredients. The first is a solvent, a medium in which the chemistry of existence can unfold. For us, that solvent is liquid water. It is a remarkable substance, seemingly simple, yet its properties are the foundation of our biology. Water is a polar molecule, meaning it has a slight electrical charge at each end, allowing it to dissolve more substances than almost any other liquid. It acts as the universal transport system within our cells, ferrying nutrients in and carrying waste out. It moderates temperature, protecting delicate biological structures from a world of extremes. We see its life-giving power in the green of a forest after rain, and feel its necessity in the simple primal urge of thirst. For a long time, the search for life beyond Earth was in essence the search for water. The second ingredient is a collection of building blocks. Life needs structure. It needs a way to create complex machinery, to build cells, to store information, to replicate. On Earth, the master architect of this machinery is the element carbon. Of all the elements in the universe, carbon is uniquely suited for this role. It possesses a remarkable ability to bond with 4 other atoms simultaneously, including other carbon atoms. This allows it to form long, stable, and intricate chains, rings and branching structures. It is the ultimate biological Lego brick. From the simple scaffolding of a sugar molecule to the breathtaking complexity of a DNA helix, carbon provides the backbone. It is so central to our biology that we call ourselves carbon-based life forms. We are, in the most literal sense, beings of stardust assembled from the carbon forged in the hearts of long-dead stars. The third and final ingredient is energy. A blueprint and building materials are nothing without a force to assemble them. Life is not a static state. It is an active, ongoing process that fights against disorder. This requires a constant source of power. On Earth's surface, that energy comes overwhelmingly from our star, the Sun. Sunlight, captured through the elegant process of photosynthesis, fuels the vast majority of our planet's ecosystems. Plants convert light into chemical energy, and that energy flows up the food chain, powering everything from the smallest insect to the largest whale. It is the engine that drives the great interconnected web of terrestrial life. Liquid water, organic carbon molecules, and a reliable energy source. For centuries, this was our non-negotiable checklist for a life-bearing world. If a planet had these 3 things, it was a candidate. If it lacked even one, it was deemed barren. But our own world has secrets. It has hidden laboratories where life has been conducting experiments in the dark, under crushing pressure, and in searing heat for eons. These experiments reveal that the blueprint of being is far more flexible, more resilient, and more creative than we ever dared to imagine. To find these places, we must travel to the most inhospitable environments on Earth, places that look more like an alien world than our gentle green home. Let us journey first to the deep ocean floor, miles beneath the waves, to a place the sun has never touched. The pressure here is immense enough to crush a submarine like a tin can. The water is near freezing, and the darkness is absolute. By our old checklist, life should not exist here. There is no sunlight to provide energy, and yet it does. Here, clustered around hydrothermal vents, great volcanic fissures in the ocean floor, thrives one of the most alien ecosystems on our own planet. These vents spew out a cocktail of superheated water and minerals from deep within the Earth's crust, black clouds of sulfur and chemicals. This is not a gentle source of energy. It is a violent chemical furnace, and the life here has learned to harness it. Giant tube worms, some taller than a human with no mouth and no stomach, wave their blood-red plumes in the dark water. They are packed with bacteria that perform a miracle called chemosynthesis. Instead of using sunlight, these bacteria use the chemical energy of hydrogen sulfide, a compound toxic to us, to create sugars and fuel an entire ecosystem. They have built a world without the sun. They show us that the category of energy source is far broader than we once thought. A star is not the only engine that can power life. Now let us travel to another extreme, the Atacama Desert in Chile, one of the driest places on Earth. Here years can pass without a single drop of rain. The soil is so arid and salty that it resembles the surface of Mars. The sun's ultraviolet radiation is brutal and unfiltered. Here, our second ingredient, liquid water, is almost entirely absent. Yet life persists. It has simply learned to hide. If you were to crack open one of the pale, unassuming rocks scattered across the desert floor, you might see a thin, greenish line just beneath the surface. These are endoliths, communities of microorganisms that live inside the rock. The rock itself acts as a shield against the deadly UV radiation, and it traps what little moisture comes from fog or the air itself. These organisms live their entire lives on a timescale we can barely comprehend, metabolizing so slowly that they seem suspended between life and death. They prove that life doesn't always need an ocean or a river. Sometimes a whisper of humidity trapped in stone is enough. Finally, let's consider an organism that challenges our very definition of resilience. Its name is Democritus radiodurans. It is a simple bacterium, but it has been nicknamed Conan the Bacterium for its almost unbelievable toughness. This microbe can withstand doses of radiation thousands of times greater than what would be lethal for a human. It can survive extreme cold, dehydration, vacuum, and acid. Its true superpower is its ability to repair its own DNA. When blasted with radiation, that would shatter the genetic code of other organisms into millions of pieces. Democritus, calmly and methodically, stitches its own chromosomes back together, good as new. It does not resist the damage, it simply endures it and rebuilds. This tiny organism teaches us the most profound lesson of all, that the boundary between a habitable environment and a lethal one is not a sharp line, but a gradient. Life, once it takes hold, is a force of incredible tenacity. It doesn't just survive in the margins, it redefines them. These organisms, these extremophiles, are not mere curiosities. They are messengers from the edges of possibility. They are Earth's way of telling us to think bigger. They force us to take our neat little checklist, liquid, water, carbon, energy, and add question marks to every item. Water might be the ideal solvent, but could another liquid work? On Saturn's moon Titan, for instance, there are vast lakes and rivers, not of water, but of liquid methane and ethane. At those cryogenic temperatures, could a different kind of chemistry, a slower and stranger biology arise? Carbon might be the perfect building block for us, but could another element play that role? Silicon sits just below carbon on the periodic table. It too can form 4 bonds, suggesting it could create complex molecules. A silicon-based life form is a staple of science fiction, but it is rooted in a real chemical possibility. Its biochemistry would be utterly alien. Instead of breathing out gaseous carbon dioxide, it might exhale solid silicon dioxide, essentially sand. It would be a creature of crystal slow and geologic thriving in an environment we would find utterly toxic. This entire field of inquiry, this blend of biology, chemistry, and astronomy, is known as astrobiology. It is the science of asking "what if" on a cosmic scale. It uses the one data point we have, life on Earth, to extrapolate the vast unknown potential of life everywhere else. Astrobiologists look at the extremophiles in deep-sea vents and see a model for life on Jupiter's moon Europa, which is believed to have a vast liquid water ocean beneath its icy shell, potentially warmed by tidal forces and dotted with similar chemical vents. They study the microbes in the Atacama Desert and wonder if similar life could be hiding inside rocks on Mars, shielded from the harsh surface radiation. The blueprint of being we are learning is not a single rigid document. It is more like a vast library of possibilities, and we have only read the first book. The fundamental principles may be the same. Everywhere life will always need a solvent, building blocks, and energy. But the specific forms those ingredients take could be as varied as the worlds they inhabit. Life is not a fluke. It is a fundamental property of complex chemistry, a pattern that matter falls into when the conditions are right. And our extremophiles show us that the right conditions are far more diverse and widespread than we ever knew. We have held the blueprint in our hands and found its edges to be soft, its rules bendable. We see that the potential for life might be woven into the very fabric of chemistry itself, an emergent property of the universe as natural as the formation of a star or a planet. But this realization brings with it a profound, almost overwhelming question. If the ingredients are common and life is this tenacious, how do we begin to estimate the chances of it arising elsewhere? How do we move from possibility to probability? How do we take this vast star-filled void and begin to organize our search to systematically map our own ignorance? To do so, we need more than just a blueprint for life. We need a framework for the search itself. We need a cosmic calculation, an equation designed not to give us a final answer, but to give structure to our wonder and to guide our questions as we turn our eyes back to the heavens. Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet history of strange and forgotten creatures, teaches us that even here, the forms of life are more varied than we could ever imagine. To seek only our own reflection in the cosmos might be the surest way to miss a neighbor waving from a different kind of window. And so, we are faced with a question of staggering scale. A question that can easily paralyze the mind with its sheer immensity. How do you begin to count the uncountable? How do you estimate the number of intelligent civilizations that might exist in our galaxy when you have only one example to study ourselves? In 1961, in a quiet conference room in Green Bank, West Virginia, a young radio astronomer named Frank Drake decided to approach this monumental question not with a grand philosophical statement, but with a tool of humble and beautiful logic. He didn't claim to have the answer. Instead, he proposed a way to organize our ignorance. He laid out a chain of probabilities, a sequence of questions that, if we could answer them one by one, would lead us toward a reasonable estimate. This tool became known as the Drake equation. It is not a machine for calculating a definitive number. It is a mirror reflecting what we know, what we guess, and what remains shrouded in the deepest mystery. It is like a vast cosmic puzzle, and Drake simply gave us the list of pieces we need to find. Let us assemble this puzzle together, piece by piece, and see what picture begins to form. The first piece of the puzzle is perhaps the grandest in scale. It is called R star, the rate of star formation in our galaxy. How many new suns are born each year from the swirling clouds of gas and dust that drift through the Milky Way? This isn't a number we must simply guess. We can look up. We can use our telescopes to peer into stellar nurseries, vast nebulae, where gravity is pulling matter together, igniting the fires of new stars. We can measure the light of the galaxy, estimate its mass, and model its life cycle. From this, astronomers have arrived at a surprisingly modest number. The current estimate is that our galaxy, with its hundreds of billions of stars, creates only a few new ones per year, perhaps 3 to 7. It is a slow, majestic process. This first piece of the puzzle, the foundation of everything, is a knowable quantity. It feels solid in our hands. It gives us a starting point, a reliable rhythm for the cosmic engine. The next piece fits neatly beside the first. It is called FP, the fraction of those newly formed stars that have planets orbiting them. For most of human history, this was a matter of pure speculation. We knew of the planets in our own solar system, but were they a cosmic fluke? A rare exception? Or was it the rule that stars should have companions? In the last few decades, this question has been answered with breathtaking clarity. Thanks to instruments like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, we have discovered thousands of exoplanets. We have learned that planets are not rare at all. They are common. In fact, it seems that almost every star has at least one planet. Some have many more. This puzzle piece, once a blurry guess, has sharpened into focus. We can now say with confidence that the vast majority of stars are not solitary wanderers. They are the centers of solar systems, each a potential stage for some new story. The universe, it seems, is generous with its worlds. With stars and planets in place, we reach for the third piece of our puzzle. This is NE, the average number of planets per solar system, with planets that are suitable for life. Here, our certainty begins to soften at the edges. What, after all, makes a world suitable? We tend to think of the Goldilocks zone, a region around a star where the temperature is just right, not too hot and not too cold for liquid water to exist on a planet's surface. Water, as we understand it, is the universal solvent, the medium in which the complex chemistry of life can unfold. Our own Earth orbits comfortably within our Sun's Goldilocks zone. Based on our exoplanet discoveries, we estimate that a significant fraction of stars, perhaps 1 in 5, have an Earth-sized planet in this habitable zone. This piece of the puzzle seems to fit. It suggests that there are billions of worlds in our galaxy alone that have at the very least a fundamental prerequisite for life as we know it. But even here, we must be humble. Perhaps life can exist in the methane lakes of a moon, like Titan, or in the subsurface oceans of a frozen world, like Europa, far outside the traditional habitable zone. Our definition of suitable may be a failure of imagination. For now, however, we place this piece in our puzzle, and the picture it helps to form is one of a galaxy brimming with potential homes. And it is here, as we reach for the fourth piece, that our hands begin to tremble. The solid ground of astronomy gives way to the deep, murky waters of biology. This next piece is FL, the fraction of those suitable planets where life actually arises. We have put a stage in place, a warm, wet world orbiting a stable star. But does the play always begin? This is the question of abiogenesis, the leap from non-living chemistry to living biology. On Earth, we know it happened. Sometime in the primordial oceans, a collection of molecules crossed a threshold, becoming self-replicating, metabolizing, and evolving. It happened at least once. But was that event a near certainty, an inevitable outcome of planetary chemistry? Or was it an astronomical stroke of luck, a chemical accident so improbable it might never have happened anywhere else? We simply do not know. We have only one data point ourselves. This piece of the puzzle is a void. It could be a large welcoming shape suggesting life is a cosmic imperative. Or it could be a sliver so thin, so impossibly specific that it barely exists at all. All of science hangs on this question. Let us assume for the sake of our thought experiment that the leap is made. Life has begun. We now reach for the fifth piece, Phi, the fraction of those life-bearing planets, where that life evolves to become intelligent. Look at the history of life on Earth. For billions of years, our planet was home only to single-celled organisms. The dinosaurs ruled for 150 million years, a vast stretch of time, yet they did not build radio telescopes. Intelligence of the kind that can ponder the cosmos is a very recent and perhaps very fragile branch on the tree of life. Is it an inevitable evolutionary trend, a useful survival strategy that will eventually appear given enough time? Or is it like the peacock's tail, a bizarre and beautiful accident, a path taken only once? Perhaps most life in the universe is microbial. Perhaps the galaxies are filled with endless silent forests and oceans rich with creatures, but with no one to look up at the stars and wonder. This puzzle piece, like the last, is a guess. Its shape is defined more by our philosophy than by our data. And even if intelligence arises, there is another hurdle. The sixth piece is Fc, the fraction of those intelligent civilizations that develop a technology that is detectable from space. A society of intelligent dolphins might have poetry and philosophy, but their songs would never leave their ocean. A civilization of beings who never discover electricity or radio waves would be invisible to our searching ears. To be counted in the Drake equation, a civilization must not only think, it must shout. It must manipulate the electromagnetic spectrum, beaming signals out into the void, intentionally or not. This step from consciousness to communication is a technological and sociological one. Is the drive to build and broadcast a universal trait of intelligence or a peculiar habit of a single species of primate on a small rocky world? This piece of the puzzle is about the choices a civilization makes, and we have no way of knowing what choices others might make. Finally, we arrive at the last piece of the puzzle, and it may be the most important and most sobering of all. It is a single letter L. It stands for the length of time that a communicative civilization survives and continues to send signals into space. This isn't a fraction. It's a duration. Does a typical technological civilization last for a few centuries before succumbing to war or climate change or self-inflicted catastrophe? Or does it achieve stability and survive for millions of years, becoming a permanent shining light in the galactic darkness? The history of humanity suggests that this number could be tragically short. We have only been a communicating civilization in the radio sense for about a century. How much longer will we last? The value of L determines whether the galaxy is filled with the ruins of forgotten empires or is alive with enduring wise contemporaries. This final piece of the puzzle forces us to look back at ourselves, to confront our own fragility. And so the puzzle is assembled. We look at the final picture, and its meaning depends entirely on the shapes we chose for those unknown pieces. If we are optimistic, if we assume that life is common, intelligence is a likely outcome, and civilizations can last for a long time, then the Drake equation yields a spectacular result. The number of communicating civilizations in our galaxy N could be in the hundreds of thousands, or even millions. The cosmos would be a bustling, noisy place, a chorus of voices echoing between the stars. But if we are pessimistic, if we assume that the leap from chemistry to life is a near impossibility, or that intelligence is a one-time fluke, or that all civilizations inevitably destroy themselves in their technological infancy, then the equation gives us a very different and very lonely answer. N could be 1, just us. The power of the Drake equation is not in its answer, but in its structure. It shows us that the question, "Are we alone?" is not a single question, but a series of smaller, more manageable ones. It is a roadmap for future research, telling us what we need to learn about stars, planets' biology, and even sociology to find our way. It has transformed a philosophical yearning into a scientific discipline. It gives us a framework for hope, a calculation that suggests we should, by all reasonable accounts, have company. Even with conservative guesses for the unknown factors, the sheer number of stars and potential homes suggest that the number n should be greater than 1. The math implies that someone somewhere should be out there. The puzzle we have assembled, even with its missing pieces, paints a picture of a galaxy that should be at the very least murmuring with signals. And so, with this cosmic calculation in hand, we turn our instruments to the sky. We listen, we watch, we expect an echo. We have run the numbers and they point to a universe filled with possibility. But all we hear is silence. Before we venture further into the star-strewn darkness, let us return home. Not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believe the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet history of extinctions and explosions of diversity, hints that the story is far more strange. And so, armed with a humble understanding of what life might be, we turn our gaze back to the cosmos and we listen. But in that listening, we encounter not a chorus, but a question so profound it has come to haunt the search for cosmic company. It is a question born not of complex data, but of a simple, jarring observation. It began as many great thoughts do over a casual lunch. The year was 1950. The place the Los Alamos National Laboratory, a site already steeped in the weight of world-changing equations. The brilliant physicist Enrico Fermi was walking to lunch with his colleagues, animatedly discussing a recent cartoon in The New Yorker that depicted cheerful aliens disembarking from a flying saucer. The conversation was light, a brief respite from the heavy work of the atomic age. They talked of the feasibility of faster-than-light travel, of the probability of Earth-like planets. The numbers, even with the limited knowledge of the time, were staggering. Our galaxy alone, a swirling disk of stars, was estimated to contain hundreds of billions of suns. And the universe they knew held hundreds of billions of such galaxies. The conversation flowed, and they sat down to eat. The clinking of cutlery filled a momentary pause. And then, out of the blue, Fermi looked up at his friends and asked a question of just 3 words. A question so simple, yet so devastatingly powerful, that it sliced through all the optimistic mathematics. He asked, "Where is everybody?" His colleagues laughed, but Fermi was serious. He began to reason aloud, performing one of his famous back-of-the-envelope calculations. The universe is ancient, over 13 billion years old. Our own galaxy has been patiently turning for at least 10 billion of those years. If you consider the sheer number of stars, many of them far older than our own sun, and then consider the likely number of planets orbiting them, the number of potential cradles for life becomes astronomically large. It's a number that defies easy comprehension, like trying to imagine a single grain of sand on all the beaches of the world. From there, the logic seems to unfold like an undeniable truth. If even a tiny fraction of these planets developed life, and a tiny fraction of that life became intelligent, and a tiny fraction of that intelligent life developed technology, then the galaxy should be teeming. It should be loud. Given the immense head start that any civilization around an older star would have millions or even billions of years, they would have had more than enough time to master interstellar travel even at slow conventional speeds. In a few million years, a single civilization could colonize the entire Milky Way, leaving signal structures or artifacts everywhere. Their presence should be as obvious as a city's lights seen from a distant hilltop. And yet, when we look, we see nothing. We hear nothing. The radio telescopes those patient cupped ears turn to the heavens pick up only the ancient whispers of cosmic background radiation, the static of pulsars, the dying sighs of distant galaxies. There are no engineered signals, no beacons, no interstellar chatter. The sky is silent. This is the heart of the Fermi Paradox. It is a gaping contradiction between a high probability and a complete lack of evidence. It is the story of a grand cosmic party. The invitations were sent out with the Big Bang itself written in the laws of physics and chemistry. The venue is unimaginably vast, with trillions upon trillions of rooms each, a solar system with its own unique potential. The party has been going on for billions of years, more than enough time for countless guests to arrive. We humanity are like a guest who has just shown up a little late perhaps, but eager to mingle. We walk into the grand ballroom decorated with the swirling nebulae and glittering star clusters, and we find it empty. The lights are on, the music of the spheres is playing, but the hall is utterly, profoundly vacant. We check our invitation. The date seems right. The address is correct. But there is no one here. And so we are left to stand in the doorway and whisper into the immense silence. Where is everybody? The implications of this silence ripple outward, touching the very core of how we see ourselves and our place in the universe. It forces us to confront possibilities that are as awe-inspiring as they are unsettling. Each potential answer is a universe of its own. Perhaps the most straightforward, and for many, the most lonely conclusion, is that we are simply alone. Perhaps the chain of events that led from non-living matter to a thinking, tool-using species is so fantastically improbable, a series of cosmic lottery wins, so unlikely that it has happened only once. In this entire sprawling galaxy, with its 400 billion stars, this one small blue world is the only place where consciousness has ever looked up and wondered. If this is true, then the silence is not a mystery. It is the natural state of things. The universe is not a bustling city. It is a vast, beautiful, and sterile wilderness, and we are its sole miraculous inhabitants. The weight of that thought is immense. It would mean that all the art, all the music, all the questions, all the love and all the loss of the cosmos are contained here on this fragile sphere. The future of cosmic consciousness would rest entirely on our shoulders. Or there is a second possibility, one tinged with a different kind of pressure. Perhaps we are not alone, but simply first. Perhaps the conditions for intelligent life have only recently become favorable in the galaxy. Maybe older star systems were too chaotic, too rich in deadly radiation from supernovae for complex life to get a foothold. In this scenario, we are not the lonely exception, but the pioneers. We are the first guests to arrive at the party, the ones who get to turn on the lights and put out the decorations. The silence we hear is not an eternal emptiness, but the quiet before the dawn. Other civilizations may be stirring now on other worlds, blinking in the light of their own suns. They are out there, but they are our contemporaries, not our ancient ancestors. They are just as mystified by the silence as we are. But there is a third category of possibilities, and it is here that a shadow falls. This is the idea that we are neither alone nor first, but that something else is at play, something unseen and perhaps unknowable. Perhaps the galaxy is full of advanced civilizations, but they are deliberately quiet, hiding from some unknown predator or adhering to a cosmic rule of non-interference. We might be living in a kind of cosmic nature preserve, an isolated nursery, watched over by silent guardians who have declared Earth off limits. In this view, the silence is not empty, but intentional. It is a curtain drawn across a stage we are not yet ready to see. Or more chillingly, perhaps advanced civilizations do not last. Perhaps technology itself contains the seeds of its own destruction. Be it through nuclear war, ecological collapse, or a rogue artificial intelligence, it might be the universal fate of intelligent species to flicker into existence for a brief, brilliant moment before self-immolating. In this dark forest, a civilization that broadcasts its existence is like a lost child shouting in the woods at night, attracting predators. The silence in this case is the sound of wisdom, the wisdom of those who know to stay hidden. The empty ballroom of the cosmos is not empty because no one was invited, but because the previous guests have all met a terrible end. For decades, we have stared at this paradox, this great silence, turning it over and over in our minds. It is the ultimate detective story with a universe-sized crime scene and no clues. The absence of evidence becomes in itself a form of evidence. The silence is not a passive void. It has a character. It is a presence that demands an explanation. Every star we map, every exoplanet we discover, only sharpens the teeth of the paradox. The more we learn about how common planets are, the more we understand the tenacity of life on our own world, the louder the silence becomes. Enrico Fermi's simple question, "Where is everybody?" has fractured into 1,000 others. Are we the first, the last, the only? Are we isolated? Are we being watched? Or is there some fundamental barrier, some cosmic law we have yet to discover that prevents the universe from filling up with life? The party seems ready, the stage is set, but something is preventing the guests from arriving. Perhaps the silence is not a sign that something is wrong, but rather a testament to how profoundly difficult the journey is. Perhaps the path from a cooling planet with simple chemistry to a star-faring civilization is not a gentle upward slope, but a treacherous climb over a series of near-impossible obstacles. It may be that this path is littered with hurdles so formidable, so utterly impassable, that almost no one ever makes it all the way to the end. Before we can consider who might be hiding or who might have come before, we must first confront the daunting possibility that the ballroom is empty, for the simplest reason of all: almost nobody survives the journey to get here. We must consider the possibility of a great filter. Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet majesty and its apparent solitude, might be telling us a different story. It might be whispering that its existence is not a rule, but a breathtaking exception. This brings us to one of the most sobering and profound answers to Fermi's question. Perhaps the reason the universe seems so empty is because it is empty. Perhaps the silence is not a mystery to be solved, but the natural state of things. This line of reasoning leads us to a concept known as the Great Filter. Imagine the history of life from the first spark of chemistry to a galaxy-spanning civilization as a long and treacherous journey. This journey is not a smooth path, but an obstacle course, a series of gates that must be passed. Each gate represents a critical evolutionary or developmental step, the leap from non-living matter to the first replicating molecule, the jump from simple cells to complex ones, the emergence of consciousness, of tool use of science. The Great Filter hypothesis, proposed by the economist Robin Hanson, suggests that at least one of these steps is fantastically, almost impossibly difficult. So difficult, in fact, that countless potential life forms on countless worlds stumble and fall, never to rise again. The filter is the gate where nearly everyone fails. The silence we hear across the cosmos is the sound of that failure, the sound of a universe full of journeys that were cut short. The question then is a chilling one. Where is this filter? Is it in our deep past, a hurdle we have already miraculously cleared? Or is it looming in our future, a final test we have yet to face? Let us first consider the optimistic view that the Great Filter is behind us. This is the foundation of what is known as the rare earth hypothesis. It argues that we are not just fortunate, but the winners of a cosmic lottery of such staggering unlikelihood that we might as well be alone. The silence is the sound of our own unique triumph. The filtering may have begun before our planet even formed. Life as we know it requires a stable environment, and that stability starts at a galactic scale. Our solar system resides in what is called the galactic habitable zone, a narrow, peaceful ring partway out from the galaxy's chaotic center. Too close to the core, and the lethal radiation from the supermassive black hole and the constant supernovae would sterilize any nascent life. Too far out in the galactic suburbs and the sparse distribution of heavy elements. The iron, carbon, and oxygen forged in stellar furnaces would make the formation of rocky planets and organic molecules impossible. We are in the cosmic Goldilocks zone, not too violent, not too barren. That is the first gate. Then comes the star itself. Our Sun is a remarkably stable G-type main sequence star. It burns with a steady, enduring light, neither prone to the violent planet-scorching flares of smaller red dwarfs, nor so massive that it would burn out in a mere few million years long before complex life could ever evolve. It is a quiet, reliable parent star, providing the gentle, consistent energy needed for the slow, patient work of evolution. Another gate successfully passed. Zooming closer, we find our own planetary neighborhood, and the filters become even more specific. Earth is not alone in its dance around the sun. It has guardians. Chief among them is Jupiter, the colossal gas giant whose immense gravity acts as a cosmic bouncer. For billions of years, it has swept the inner solar system clear of rogue asteroids and comets, deflecting or absorbing countless impactors that would have otherwise struck our world, causing mass extinctions that could have reset the evolutionary clock to zero. Without Jupiter, our planet's surface might be a crater-pocked, lifeless wasteland. And then there is our moon. Most planets either have no moons or a collection of small, captured asteroids. Our moon is different. It is enormous relative to our planet, likely formed from a cataclysmic collision in the solar system's youth. This oversized companion does more than light up our night sky. Its gravitational pull stabilizes Earth's axial tilt, preventing wild, chaotic swings in our planet's orientation to the sun. Without the moon, Earth's poles might wander to its equator and back again over geological time, creating unimaginably extreme climate shifts that would make the development of stable ecosystems impossible. Our steady seasons, the predictable tides, the very rhythm of life on Earth are all gifts from this ancient, violent collision. Even the planet itself is a marvel of improbability. It has active plate tectonics, a planetary engine that recycles the crust, regulates carbon dioxide in the atmosphere through a vast geological cycle, and creates the diverse patchwork of continents and oceans. This constant churning is vital for maintaining a stable climate over eons. It prevents a runaway greenhouse effect like the one that turned Venus into a furnace, or the deep freeze that seized Mars. Many rocky worlds may be geologically dead, their surfaces static and unchanging for billions of years. Our world is alive, breathing with a fire in its core. Each of these conditions, the right galaxy, the right star, the right planetary system, the right moon, the right geology, is a potential filter. For intelligent life to arise, a planet might need to pass through all of these gates. If even one of them is exceptionally rare, then worlds like ours could be sprinkled across the universe like single grains of sand in a vast desert. But perhaps the greatest filter of all lies not in the stars or the stones, but in biology itself. For the first 2 billion years of life on Earth, the planet was inhabited solely by simple, single-celled organisms called prokaryotes. They were life, certainly, but they were stuck in an evolutionary rut. Then, in a moment, that is still one of science's greatest mysteries, something incredible happened. 2 of these simple cells merged in a symbiotic union. One cell engulfed another, but instead of digesting it, it put it to work. This new composite organism was the first eukaryotic cell, a cell with a nucleus and specialized internal machinery like the mitochondria that act as tiny power plants. This single event, which may have happened only once in our planet's entire history, was the gateway to all complex life. Every plant, every animal, every fungus, every one of us is a descendant of that one improbable merger. It was the biological equivalent of inventing the engine. Before it, life could only drift. After it, life could build empires. If this leap from a simple cell to a complex one is the great filter, then the universe might be teeming with microbial slime on countless worlds, all waiting for a spark of cellular revolution that may never come. We passed through that gate, and in doing so, left an entire universe of simpler life behind. And what of intelligence? The kind of abstract tool-using, language-driven intelligence that builds radio telescopes. For hundreds of millions of years after the rise of complex cells, our world was full of magnificent creatures. Dinosaurs ruled for 150 million years, a reign 30 times longer than our own species has existed, yet they never built a city or pondered the stars. Perhaps intelligence like ours is not an inevitable outcome of evolution, but another fluke, a rare branch on the vast tree of life. It required a specific combination of grasping hands, a vocal apparatus capable of complex sounds, a brain structure wired for social cooperation, and the environmental pressures that made these traits advantageous. Perhaps countless worlds have their own dinosaurs, their own majestic forests and dazzling reefs, but are silent because the spark of technological consciousness never ignited. If any of these past hurdles, the perfect planet, the crucial moon, the symbiotic cell, the clever mind, was the great filter, then we can breathe a sigh of collective relief. We are the survivors. We are the children of cosmic improbability. The universe is vast and empty, but it is ours to explore. The silence is not a threat, it is an invitation. But there is another possibility, one far more unsettling. What if the easy part is over? What if the truly difficult gate, the great filter, is not in our past, but in our future? This thought casts the cosmic silence in a much darker light. It suggests that the path from simple life to technological intelligence might be fairly common, that countless civilizations on countless worlds have risen just as we have. They too looked up at their night skies, built instruments to listen, and wondered if they were alone. And then, at a stage of development remarkably similar to our own, they vanished. In this scenario, the silence is a graveyard. It is the sound of a universal test that everyone so far has failed. What could such a filter be? The possibilities are born from our own headlines and our deepest anxieties. The discovery of nuclear fission provides a species with nearly limitless energy, but it also gives it the power of self-annihilation in a flash of light and fire. Perhaps every young civilization discovers this power, and few, if any, possess the collective wisdom to manage it. Or perhaps the filter is more gradual. A civilization learns to harness the energy of its planet, fueling its growth and prosperity. But in doing so, it slowly alters its own climate, poisoning its atmosphere, and oceans, triggering a runaway collapse of the very ecosystem that sustained it. The filter in this case is the challenge of achieving long-term sustainability on a finite world, a test we are currently undertaking with the outcome very much in doubt. Maybe the filter is technological. The creation of a true artificial superintelligence could lead to an exponential explosion of knowledge and capability, a utopia beyond our wildest dreams. Or it could be an existential catastrophe, an uncontrollable force, whose goals are not aligned with its creators, leading to our swift and quiet obsolescence. Perhaps the universe is silent because successful biological life inevitably creates its own more successful and non-biological successor. The filter could even be something we haven't yet imagined, a law of physics or sociology that dictates that complex societies inevitably collapse, or a cosmic danger that only becomes apparent to a civilization once it starts broadcasting its presence into the void. If the great filter is ahead of us, then our position is precarious. We may be standing on the edge of a precipice, looking out at a silent cosmos that serves as a vast cosmic warning. Every civilization before us may have reached this same point, a brief moment of technological glory before they fell into the abyss. Our apparent uniqueness is not a sign of our success, but merely a sign that our turn to face the test has come. We are not the first, only the next in line. And so, we are left suspended between two profound and opposing possibilities. One is a universe of scarcity, where we are the first, the rarest of gems, and the cosmos is a lonely but magnificent inheritance. The other is a universe of hubris, where we are just one of a long line of fleeting sparks soon to be extinguished, and the silence is the echo of universal failure. Both ideas are born from the same observation, an empty sky. Both attempt to explain the unnerving quiet. But these solutions, from the rare earth to the final looming filter, all share one foundational assumption: that the silence is real, because there is nobody there. They assume absence. They conclude that if we cannot see or hear anyone, it must be because no one exists, or no one has survived. But what if that assumption is wrong? What if the flaw is not in the universe, but in our search, in our own perception? What if the silence is not an absence, but a choice? What if the void is not empty, but merely quiet? What if the crowd is there, but for reasons of their own, they remain hidden from our view? Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet oceans and sun-scorched deserts, has shown us that life is a master of adaptation, a poet of possibility. If life here can be so varied from the silicon-shelled diatom to the thinking primate, then what forms might it take under a crimson sun or in a methane sea? When we expand our definition of life beyond the familiar, the universe blossoms with potential. The great silence then becomes even more profound. If the cosmos is not empty, but teeming with possibilities, then the absence of evidence feels less like a confirmation of solitude and more like a riddle. It suggests that perhaps the answer is not in the stars, but in ourselves, in the way we are looking, the questions we are asking, and the assumptions we carry. Let us imagine for a moment that we are not alone. Let us assume the great filter is behind us, that life is common, and that intelligence is a convergent evolutionary path. If this is true, then the silence is not an absence, but a choice, or perhaps a consequence. We step now into a different kind of gallery, one where the exhibits are not theories of absence, but theories of presence. Here the silence is a curtain, and we are left to wonder what or who is behind it. Our first exhibit is bathed in a soft observational light. It is a world much like our own, a beautiful swirling marble of blue and white, encased in a transparent sphere. We are looking at it, but it cannot look back at us. This is the essence of the zoo hypothesis. In this scenario, humanity is not alone, but is instead part of a cosmic wilderness preserve. We are a developing civilization, protected and observed by one or more vastly older, wiser intelligences. They are the silent wardens of the galactic garden, and we are a rare flower they wish not to disturb. The idea is both humbling and a little unsettling. It suggests a universe governed by a principle of non-interference, a cosmic prime directive. These ancient beings may have learned from their own history or from observing countless others that contact with a superior civilization is almost always disruptive, if not catastrophic, for the younger one. Our cultures, our religions, our science, all could be irrevocably shattered by the revelation of a cosmic truth we are not yet ready to comprehend. And so, they watch. They study us from afar through instruments we cannot detect, respecting our isolation as a sacred space for natural growth. The silence in this case is a gift. It is the sound of protection, the quiet hum of a carefully maintained sanctuary. Is this a comforting thought, perhaps? It would mean that we are not adrift in an indifferent cosmos, but are instead cared for, deemed worthy of preservation. But it also recasts our greatest achievements as the charming, rudimentary fumblings of a child observed by knowing adults. Our philosophies, our cosmic discoveries, our broadcasted signals all might be recorded and analyzed as fascinating yet primitive cultural artifacts. We are a subject of study, a grand experiment in planetary biology and sociology. The ethics of such a scenario are complex. Is it an act of profound benevolence to leave us alone? Or is it the ultimate act of condescension, a refusal to engage with us as equals we may never know? We can only look up at the sky and wonder if the one-way mirror is real. Let us move now to the next exhibit, where the light is dimmer and the air feels colder. The atmosphere here is one of caution, of held breath. This is the gallery of the dark forest hypothesis, a far more chilling explanation for the great silence. It takes its name from a simple, terrifying metaphor. The universe is a dark forest. In this forest, every civilization is an armed hunter moving silently through the trees. The hunter cannot know if another rustle in the leaves is a fellow hunter, a harmless animal, or a predator. Because the stakes are existential, the survival of one's entire species, the safest strategy is to assume the worst. To make a sound, to light a fire, to reveal your position in any way is to invite a swift and silent arrow from the shadows. Therefore, everyone stays quiet. Everyone hides. This hypothesis is not born of malice, but of a ruthless game theory logic. Imagine two emerging civilizations. The first is optimistic, curious, and eager to connect. It builds powerful transmitters and beams messages of greeting into the cosmos. We are here, come find us. The second civilization is paranoid, cautious, and security-oriented. It invests its resources in listening, in staying hidden, in developing defenses. Now imagine a third civilization, an ancient, powerful predator. Which of the first two is more likely to survive an encounter? The logic is brutal. The universe in this view is populated only by those who learn to stay silent and those who were silenced before they learned. The silence, then, is not the sound of an empty cosmos. It is the sound of a cosmos holding its breath. It is the discipline of survivors. Advanced civilizations would not only hide themselves, but would also actively eliminate any noisy newcomers who might attract unwanted attention to their cosmic neighborhood. A loud broadcast from a planet like Earth would be like a baby crying in the dark forest, a danger not only to itself, but to anyone nearby. We are shouting into a quiet room where everyone else is hiding under the table, and they are not pleased. This vision of the universe is a lonely one. It replaces the wonder of discovery with the pragmatism of fear. It suggests that the desire for connection is a fatal youthful flaw, and that wisdom is found in silence and concealment. We turn from the shadows of the forest and move toward an exhibit that is not an object at all, but a shimmering, indescribable field of energy and light. It hums with a complexity that our minds can barely grasp. This is the transcendence hypothesis, and it offers a silence born not of fear or caution, but of profound, unimaginable change. What if a civilization's technological and spiritual evolution doesn't just continue on our current path, but fundamentally transforms what it means to be a living entity? Consider our own trajectory. We are already beginning to merge with our technology. We are digitizing our consciousness into vast networks of information. What is the endgame of this process? Perhaps a mature civilization eventually sheds its biological shell like a chrysalis left behind. They might upload their minds into a computational substrate existing as pure information in a realm we cannot access. They might engineer their own physics, creating pocket universes with custom-tailored laws. They might merge into a single planet-sized superorganism, a collective consciousness whose thoughts span millennia. From such a perspective, our concerns, our biology, our radio waves, our physical exploration of space would seem utterly quaint. It would be like a pod of whales trying to have a meaningful conversation with a colony of ants on the seafloor. The whales exist in a world of three-dimensional currents of song that travels for hundreds of miles of a social and sensory reality so different from the ants' world of chemical trails that communication is not just difficult, it is conceptually impossible. The silence in this scenario is the silence of a different plane of existence. The signals are there, but they are not made of light or radio waves. They might be encoded in the fluctuations of dark energy, in the fine-tuning of physical constants, or in the quantum foam of space-time itself. The universe might be singing with the thoughts of transcendent beings, a symphony of consciousness we are utterly deaf to. They are not hiding from us. They are simply beyond us. We are looking for physical beings on rocky planets, and they have become the music of the cosmos itself. This is perhaps the most humbling thought of all. It suggests that the universe is not empty, but that we are not yet equipped to perceive its true richness. This brings us to our final exhibit, which is simpler and perhaps more likely than all the others. It is not as dramatic as a cosmic zoo or a dark forest, but it is just as powerful. This exhibit is simply a room full of mismatched tools. Here is a telegraph key next to a smartphone. Here is a smoke signal trying to communicate with a satellite dish. Here is a message in a bottle floating in an ocean the size of a galaxy. This is the hypothesis of scale and method. Perhaps the silence is simply a technical problem. We have been listening with our radio telescopes for less than a century. That is a microscopic sliver of cosmic time. What are the chances that another civilization, hundreds of thousands or millions of light years away, happens to be using the same technology pointed in the right direction at the exact right moment to hear our faint whispers? The sheer scale of space and time works against us. A civilization could have broadcast for 1,000,000 years and then gone silent 1,000 years before we started listening. Their signal might have passed us by while we were still developing agriculture. And what if radio is the wrong medium entirely? We consider it fundamental, but it's inefficient, slow, and noisy. A truly advanced civilization might communicate using modulated neutrinos or gravitational waves, or some form of faster-than-light communication based on physics we have yet to discover. Using radio to search for them would be like standing on a shoreline, waiting for a letter from a country on the other side of the world, while an airplane flies unnoticed overhead. The silence then might just be a profound misunderstanding of the medium. It's the universe's busiest intersection, and we are standing on the corner with a tin can and a string. They are not ignoring us. They are not hiding from us. They are not transcendent. They are simply talking a different language on a different channel at a different speed. The cosmos is not a silent void. It is a library where all the books are written in a language we cannot yet read. This gallery of possibilities leaves us in a state of deep humility. Whether we are a protected species in a cosmic zoo, a naive child in a dark forest, or a fledgling intelligence unable to perceive the true nature of reality, the conclusion is the same. The silence we perceive may say very little about the universe and a great deal about ourselves. It reflects the limits of our technology, the boundaries of our imagination, and our specific, perhaps lonely place in the grand sweep of cosmic time. Faced with this gallery of overwhelming possibilities, from cosmic benevolence to existential dread to simple, profound misunderstanding, humanity made a choice. It was a choice born not of certainty, but of hope. Instead of being paralyzed by the silence, a few quiet pioneers scattered across our small world decided to do the simplest, most audacious thing imaginable. They decided to listen. They chose to build the instruments to aim them at the silent stars and to strain to hear a whisper in the vast cosmic static. It was an act of faith and investment in the idea that someone somewhere might be worth hearing. And that is the story we turn to now. Before we venture further into the star-strewn darkness, let us return home. Not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believe the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet oceans and volcanic vents, has shown us that life is a master of adaptation, a far more versatile artist than we ever imagined. Armed with this humble, expanded understanding, the question shifts. It moves from what we are looking for to a far more practical and perhaps more daring question. How do we look? How do we even begin to search for a mind other than our own across the silent, unforgiving gulfs of space? The answer, when it came, was not born of a grand vision or a state-funded crusade. It began, as so many great endeavors do, with a quiet conversation between two thoughtful minds and a proposal so elegant in its simplicity that it would change the course of astronomy forever. The year was 1959. The world was gripped by the anxieties of the Cold War, its gaze often turned downward to borders and ideologies. But in the halls of Cornell University, two physicists, Giuseppe Cocconi and Philip Morrison, turned their gaze upward. They were not astronomers by trade, but their expertise in physics gave them a unique perspective on the cosmos. They considered the grandest question of all: are we alone, not as a matter for philosophy, but as a problem of engineering and information. If another civilization won roughly at our own technological level, or perhaps a little beyond, wanted to make its presence known, how would it do so? Their reasoning, published in the scientific journal Nature, in a paper titled "Searching for Interstellar Communications," was a masterclass in cosmic logic. They dismissed sending physical probes, for the distances are too vast and the travel times too long. They considered light, but visible light is easily obscured by the great clouds of dust and gas that drift between the stars. They needed a medium that was efficient, fast, and could travel unimpeded across the galaxy. Their conclusion pointed to one thing: radio waves, specifically microwaves. This was not a random guess. The universe, for all its spectacular violence, has regions of profound quiet. Cocconi and Morrison identified a specific band of the microwave spectrum that is remarkably free from natural cosmic noise. It's like finding a quiet channel on a radio dial filled with static. A signal sent in this band would stand out. It would be an intentional act, an anomaly against the background hum of creation. Furthermore, they proposed a specific, universally significant frequency within that band, 420 MHz. This is the natural frequency at which neutral hydrogen atoms, the most abundant element in the entire universe, vibrate and emit radio waves. Any civilization advanced enough to study the stars would know of this frequency. It is a cosmic hailing channel, a universal constant written into the very fabric of the cosmos. Their paper was a spark. It was a formal invitation to the scientific community to move the search for extraterrestrial intelligence from the realm of fiction into the domain of experimental science. It provided a roadmap. It said, "We do not need to invent fantastical technologies. We already have the tools. We have radio telescopes. All we have to do is point them at the right stars, tune them to the right frequency, and listen." It was a call to action, a challenge posed to the quiet dreamers and the patient observers of the heavens. And across the country, in a quiet valley in West Virginia, a young astronomer heard that call. His name was Frank Drake. In 1960, he was just 30 years old, a brilliant and quietly determined radio astronomer working at the newly established National Radio Astronomy Observatory in Green Bank. The observatory was a sanctuary for scientists nestled in a valley deliberately shielded from the growing cacophony of earthly radio interference. Here, enormous metal dishes were unfurled like metallic flowers, their surfaces tilted toward the sky, listening to the ancient radio whispers of distant galaxies and dying stars. Drake had been captivated by the idea of extraterrestrial life since he was a boy, a private fascination he kept mostly to himself, in a field that valued sober, verifiable data above all else. But the Cocconi and Morrison paper gave his quiet dream a foundation of rigorous science. It gave him permission to try. With a modest internal budget of just $2,000 and the cautious blessing of his superiors, Drake embarked on the first ever systematic search for extraterrestrial intelligent signals. He called it Project Ozma, a whimsical name borrowed from the ruler of the fictional land of Oz, a place, as he put it, very far away, difficult to reach, and populated by strange and exotic beings. The name captured both the fairy tale-like ambition of the project and the scientific seriousness of its execution. His instrument was the 85-foot Tattle telescope, a marvel of its time. Imagine, if you will, standing beneath it on a cool spring morning in 1960. The air in the valley is crisp, smelling of damp earth and pine. Above you, a vast solid dish of gleaming aluminum, weighing hundreds of tons, moves with a silent, graceful hum, guided by unseen machinery. It is an enormous ear cupped and aimed at the heavens. Drake and his small team would gather in the control room, a space filled with the warm, low glow of vacuum tubes and the gentle whir of magnetic tape recorders. The technology was primitive by today's standards. There were no sleek digital displays, no powerful computers to sift through the data. There was only a chart recorder, its mechanical pen scratching a wavy line on a rolling strip of paper, documenting the incoming signal. Drake chose his targets with care. He selected two nearby sun-like stars, Tau Ceti and Epsilon Eridani. They were cosmic neighbors, just over 10 light-years away, and were considered plausible candidates for hosting planets and perhaps life. For several hours each day for a period of about 4 months, the great dish would lock onto one of these stars. And in the control room, the team would simply listen. Try to imagine the profound nature of that act. For all of human history, we had looked at the stars and wondered. We had told stories, written poems, formulated myths. But this was different. This was the first time humanity had deliberately and systematically strained its ear against the cosmic static, listening for a mind. It was an act of profound humility and audacious hope. Every crackle of random noise, every hiss from the deep cold of space had to be considered. Was this it? Was this the whisper they were waiting for? The work was methodical, even tedious. The team would first point the telescope at the target star recording the signal. Then, they would move the telescope slightly away to a patch of empty sky to record the background noise. By comparing the two, they hoped to isolate any signal that was coming directly from the star's vicinity. One day, the pen on the chart recorder began to pulse. It drew a strong repeating signal, exactly the kind of artificial intelligent pattern they were looking for. For a breathtaking moment, the control room was electric, with a feeling that can scarcely be described. It was the thrill of discovery, the vindication of a life's dream, the potential end of humanity's cosmic solitude, all condensed into a few frantic heartbeats. Was this it? Was this first contact? Drake and his team scrambled to verify the signal. They checked their equipment, their coordinates. The signal was real, and it was strong. But as their investigation continued, the source was revealed to be not a distant civilization, but a secret high-altitude military experiment. It was an airplane. The moment of sublime discovery dissolved back into the familiar static of the world. Project Ozma did not find any aliens. After 150 hours of observation, the project concluded. The tapes held nothing but the natural, beautiful, and utterly silent music of the cosmos. By that measure, the experiment was a failure. But in every other sense, it was a monumental success. It proved that the search was possible. It demonstrated that we had the technology and the methodology to listen with scientific rigor. It took the question out of the realm of speculation and placed it firmly into the world of observation. Frank Drake had not opened a dialogue with the stars, but he had opened a door for human science. He had shown that we could, and therefore, that we should listen. In the years that followed, the intellectual framework for this search grew more sophisticated. The idea of the water hole emerged, a concept as poetic as it is logical. Think of the electromagnetic spectrum as a vast landscape of sound. Much of it is filled with noise, the roar of quasars, the hiss of pulsars, the crackle of distant galaxies. But in the microwave region, there is a stretch of profound quiet, a peaceful valley between two prominent peaks of noise. One peak is the radio emission from neutral hydrogen, the H in H2O. The other is the emission from the hydroxyl radical, the OH. Together, H and OH are the constituent parts of water. And in this quiet spectral valley between them, it was proposed is the perfect place for water-based life forms to meet. The waterhole became a beautiful metaphor, a natural quiet place where different species parched for communication might gather to drink from the well of cosmic knowledge. It is a frequency range that is universally obvious quiet and deeply symbolic of life as we know it. The early pioneers were not just listening randomly. They were listening in the place they thought a conversation was most likely to begin. Yet for all its scientific elegance, the burgeoning field of SETI, the search for extraterrestrial intelligence, faced immense skepticism. To many in the mainstream scientific community, it was a fringe pursuit, a waste of valuable telescope time and resources. It suffered from what was called the giggle factor. The idea of searching for little green men seemed fanciful, unserious. Securing funding was a constant battle, and its proponents were often seen as hopeful romantics rather than serious scientists. But they persisted, driven by a curiosity that refused to be extinguished. They understood that the silence they had so far recorded was not in itself an answer. Absence of evidence is not evidence of absence. The universe is vast, and our first attempts to listen were like dipping a single cup into the ocean and concluding it held no fish. The quiet dedication of those first listeners at Greenbank was not the end of the story, but the humble beginning. Project Ozma, with its single dish, its analog recorders, and its patient human operators, was the first chapter in a much grander tale. It was a single hopeful note played into an immense and silent auditorium. What they started was a relay race of curiosity passed down through generations of scientists. The tools would change, growing infinitely more powerful and complex. The scale of the search would expand from 2 nearby stars to millions. But the fundamental act would remain the same: to turn our ears to the cosmos, to filter out the noise, and to listen for the faint, ordered whisper that would tell us we are not alone. That initial quiet effort has now evolved into a global, unceasing vigil, one carried out by machines and algorithms that never sleep forever, scanning the dark, hoping to catch a single structured echo from the void. Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet oceans and volcanic vents, has shown us that life is a master of improvisation. And so the modern search for company among the stars is no longer just a philosophical dream. It has become a meticulous, technological, and profoundly patient vigil. It is a search that has moved from the quiet study into the humming control room, from the realm of pure thought to the hard reality of data. Imagine for a moment that you are standing in a remote, high-altitude valley, sheltered from the noisy chatter of human civilization. The air is thin and crisp. All around you, arranged in a graceful, sweeping spiral, are dozens of steel dishes, each one pointed toward the silent heavens. This is not a place of grand spectacle. There are no roaring rockets or dramatic countdowns. There is only the low hum of electronics and the gentle turning of motors as the dishes track their unseen targets across the sky. This is a cathedral of listening. This is the Allen Telescope Array in California, a facility built for a single extraordinary purpose: to eavesdrop on the universe. For decades, the backbone of the search has been radio astronomy. The logic is elegant and compelling. If another technological civilization wishes to make its presence known across the vastness of interstellar space, radio waves are a near-perfect medium. They travel at the speed of light. They pass through the dust and gas that obscure visible light, and they can be generated with relative ease by any society that has mastered electromagnetism. There is even a special quiet place on the cosmic dial, a band of frequencies between the natural emissions of hydrogen and the hydroxyl molecule, the constituent parts of water. Some have poetically named this the water hole, the logical place for water-based life forms to gather and talk. It is a narrow, protected band where the natural static of the galaxy is at its lowest, a cosmic quiet zone. It is here primarily that we have been listening. The Allen Telescope Array embodies a modern approach to this search. Instead of relying on one colossal dish, it combines the power of many smaller ones. Acting together, they form a single powerful instrument, a digital compound eye that can stare at a single star with great sensitivity or scan broad swathes of the sky for a transient signal. But even this dedicated array is now part of a far grander endeavor. Enter the breakthrough. Listen Project, the most comprehensive search for extraterrestrial intelligence ever undertaken. Backed by $100 million in funding over 10 years, its ambition is breathtaking. Its goal is to survey 1 million of the nearest stars, the entire plane of our Milky Way galaxy, and the 100 galaxies closest to our own. The sheer volume of data it collects is almost beyond comprehension. Let us step now from the quiet valley of dishes into the heart of the operation, the data center. Here the silence is replaced by the steady drone of servers and cooling fans. Racks of humming machines stretch out in long rows, their blinking lights a silent testament to the river of information flowing in from the telescopes. Every second the project gathers more data than all previous SETI efforts combined. This digital torrent contains the faint whispers of distant pulsars, the crackle of quasars, and the gentle hiss of the cosmic microwave background radiation, the afterglow of the Big Bang itself. And somewhere buried within this petabyte upon petabyte avalanche of cosmic noise, there might be a signal, a single orderly artificial pattern, a whisper that says, "We are here." The task of finding it is like trying to hear a single clear note played in the midst of a million simultaneous chaotic symphonies. Sophisticated algorithms running on supercomputers are the first line of defense. They are programmed to hunt for the telltale signs of technology, a signal that is narrow in frequency, unlike the broad, messy signals produced by natural astrophysics. A signal that drifts in frequency, a hallmark of a transmission coming from a planet that is rotating and orbiting its star. A signal that repeats a pattern that proves it is not just a random burst of cosmic static or a glitch in our own electronics. For every hour of observation, there are thousands of hours of computation. The vast majority of what is flagged turns out to be our own noise, a passing satellite, a distant aircraft, or even a microwave oven on the ground. The process is one of infinite patience, of eliminating everything a signal is not, in the hope of finding what it is. But the radio spectrum is not the only place we are looking. Let us leave the radio dishes behind and travel to another kind of observatory, one that waits for the sun to set. Here the domes open not to collect faint radio waves, but to search for a different kind of message, a deliberate flicker of light. This is the world of optical SETI. The reasoning is again one of cosmic efficiency. While broadcasting a radio signal in all directions is like shouting in a crowded room, sending a targeted pulse of laser light is like using a focused beam to get someone's attention across that same room. For a civilization with advanced technology, a powerful laser could briefly outshine its own parent star, creating a flash of pure monochromatic light that would be unmistakably artificial. Our telescopes are now equipped with detectors capable of spotting these fleeting nanosecond-long bursts. The challenge is immense. We must stare at a star and differentiate its natural chaotic twinkling from a single intentional pulse of coherent light. It is a search for a cosmic lighthouse, a brief and brilliant beacon sent to signal a safe harbor in the celestial ocean. This brings us to a profound shift in the search strategy. For a long time, we were listening for a deliberate hello. But what if another civilization isn't trying to contact us at all? What if they are simply living, building, and expanding, leaving behind unintentional evidence of their existence? This has opened up an exciting new field, the search for technosignatures. A technosignature is any measurable evidence of technology. It is cosmic archaeology. We are no longer just listening for a phone call. We are searching for the ruins of a city. One of the most audacious and fascinating of these potential signatures is the concept of a Dyson swarm. First proposed by the physicist Freeman Dyson, the idea stems from a simple premise: any long-lived expanding civilization will eventually require unimaginable amounts of energy. The largest and most obvious power source in any solar system is its central star. A truly advanced society might begin to construct a vast megastructure, not a solid shell, but a massive orbiting swarm of solar collectors to capture a significant fraction of its star's energy output. From our distant vantage point, such a structure would be detectable. It would block some of the star's visible light, causing it to dim or flicker in strange aperiodic ways. More importantly, any machine that consumes energy must also radiate waste heat. A Dyson swarm would make its parent star glow unnaturally brightly in the infrared part of the spectrum. We are now actively scanning astronomical survey data, looking for stars that exhibit these peculiar characteristics, a signature of cosmic scale engineering. But not all technosignatures need to be so grandiose. Some could be far more subtle, and perhaps a little closer to home. Consider the atmosphere of our own planet. For 2 billion years, it contained significant amounts of oxygen only because life, photosynthetic organisms, was constantly pumping it out. Oxygen is a biosignature. In the same way, an industrial civilization might leave an industrial signature. Imagine analyzing the light from a distant exoplanet as it passes through its atmosphere. If we were to detect the spectral fingerprint of artificial compounds, chemicals like chlorofluorocarbons or CFCs, which do not occur naturally and can only be produced by industrial processes, it would be a staggering discovery. It would be the detection not just of life, but of a civilization that manufactures, builds, and perhaps even pollutes. It would be a quiet chemical whisper of technology across the light years. The search in all its forms is a monumental task, generating far more data than a few teams of scientists could ever hope to analyze. And this is where the search becomes a uniquely human story. For many years, a project called SETI Home invited anyone with a computer to take part. It was a brilliant solution to an impossible problem. Parcels of data from the radio telescopes were sent out across the internet to millions of volunteers. While they worked, wrote, or slept, their personal computers would use their idle processing power to scan for signals, their screensavers displaying a mesmerizing graph of the cosmic static they were analyzing. It was a global distributed supercomputer powered by collective curiosity. It transformed the lonely vigil of the astronomer into a shared human quest. While the project is now in hibernation, its legacy is profound. It proved that millions of people, united by a simple but powerful question, were willing to donate their own small piece of the digital world to the great listening. So this is the modern search, a multifaceted, technologically sophisticated, and deeply patient endeavor. We are scanning the heavens with arrays of radio dishes, their digital ears tuned to the quiet frequencies of the waterhole. We are watching for the briefest flash of an interstellar laser. We are sifting through vast archives of astronomical data, looking for the shadow of colossal engineering projects or the chemical traces of industry. We are using every tool at our disposal to scan the darkness, not for a monster, but for a mind. In all of this, we have been the silent listeners. We stand on the shore of the cosmic ocean, our instruments cupped to our ears, straining to hear a voice carried on the waves. We wait, we analyze, we hope. But this patient posture raises a new and perhaps more unsettling question. What if every shore is silent, simply because everyone is listening? What if, on 1,000 other worlds, other patient observers are also waiting for a signal to arrive? This forces us to turn the question back upon ourselves. If we are so desperate to know we are not alone, should we remain silent? Or is it time for us to do more than just listen? Is it time for us to pick up a bottle, compose a message of our own, and cast it into the void? Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations, we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet history of strange and forgotten biology, teaches us humility. It suggests that the forms life can take are far broader than our limited imagination can conjure. And so we listen. We scan the heavens with our vast electronic ears, straining for a whisper that is not our own, a signal that does not echo the familiar patterns of nature. The search for extraterrestrial intelligence, or SETI, has for decades been an act of profound patience. It is a vigil kept in the dark, predicated on the hopeful assumption that someone somewhere is doing the opposite, that they are not listening, but broadcasting. This simple reversal of roles opens a door to one of the most profound and unsettling questions our species has ever faced. While we have spent generations listening, a quieter, more contentious debate has simmered in the background. It is a debate not about what we might hear, but about what we should say. It asks, should we be content to merely listen at the edge of the cosmic ocean? Or should we gather our courage, craft a message, and cast our own bottle into the interstellar currents? This is the pivot from a passive search to an active one, a field known as METI messaging extraterrestrial intelligence, and it transforms us from silent observers into potential actors on a galactic stage whose rules we do not know. In the autumn of 1974, humanity decided for a brief and brilliant moment to shout. From the enormous jungle-cradled dish of the Arecibo Observatory in Puerto Rico, a beam of radio waves was aimed toward the heavens. Its target was a dense globular cluster of stars known as M13, some 25,000 light-years away. The message itself was a masterpiece of cosmic brevity, a digital pictogram designed by Frank Drake and Carl Sagan. Encoded in binary, it was a simple, elegant string of 1/679 bits. If an alien intelligence arranged these ones and zeros into a grid of 23 columns and 73 rows, an image would appear. It was our first serious attempt at a cosmic self-portrait. There, in stark black and white, were the numbers 1 through 10, showing our counting system. There were the atomic numbers for the essential elements of life as we know it: hydrogen, carbon, nitrogen, oxygen, and phosphorus. Below that, the chemical formulas for the sugars and bases in our DNA, followed by the iconic double helix itself. A simple stick-like figure of a human being stood in the center, flanked by its height and the population of Earth at the time. Below our figure was a diagram of our solar system with the third planet offset, indicating our home. And at the very bottom, a representation of the Arecibo dish that sent the signal, a signature, on our cosmic postcard. The entire transmission lasted less than 3 minutes, a fleeting pulse of information traveling at the speed of light toward a destination it will not reach for millennia. And should anyone there receive it and choose to reply, another 25,000 years would pass before their answer reached us. By then, our languages, our societies, our very species may be unrecognizable if we exist at all. So the Arecibo message was not truly a bid for conversation. It was a symbol. It was a technological demonstration, a declaration of capability. It was a cry of "here we are," hurled into the void, more for our own benefit than for any imagined recipient. It was a gesture born of the same impulse that led ancient peoples to carve their likenesses into stone, a desire to mark our existence, to say that for a moment in this corner of the galaxy, a species looked up and wondered if it was alone. But a pictogram, however clever, is a cold and sterile thing. It speaks of our chemistry, our numbers, our location. It does not speak of our soul. 3 years later, in 1977, humanity tried a different approach. This time, the message was not a shout, but a song. It was not aimed at a specific star, but cast adrift on a journey with no final destination. This was the Voyager Golden Record, a pair of phonograph records made of gold-plated copper, affixed to the sides of the Voyager 1 and 2 spacecraft. These probes were destined to explore the outer planets of our solar system, and then, their primary mission, complete to drift forever through the silent, empty spaces between the stars. They were, and still are, humanity's farthest flung emissaries. The records they carry are perhaps the most ambitious and romantic time capsules ever created. A committee led by Carl Sagan was tasked with an impossible challenge to distill the entire human experience into a collection of sights and sounds that could, in principle, be understood by a civilization with no concept of who or what we are. What do you choose to represent everyone? What music, what images, what greetings can possibly speak for a planet of billions? The result is an extraordinary archive of life on Earth. There are 115 images encoding everything from the structure of DNA and human anatomy to pictures of forests, deserts, cities, and families from cultures across the globe. There are the sounds of nature, wind and rain, the calls of birds and whales, the crackle of a fire. And there are the sounds of humanity, the rhythmic clang of a blacksmith, the roar of a train, the tender sound of a mother's first words to her newborn, and the electrical signals of a human brain thinking. There are greetings spoken in 55 languages, ancient and modern, beginning with Akkadian spoken in Sumer some 6,000 years ago, and ending with the modern Chinese dialect of Wu. Each is a short, hopeful salutation. "Greetings to our friends in the stars," says one. "We hope someday, having solved our own problems, we can join a community of galactic civilizations." And then there is the music. Nearly 90 minutes of it, a soaring, eclectic mix intended to convey the depth of human emotion. There is the mathematical purity of Bach, the transcendent sorrow of Beethoven, the joyful swagger of Chuck Berry's Johnny B. Good, and the haunting melodies of panpipes from Peru and vocal chants from New Guinea. It is a playlist for the cosmos, a testament to our capacity for creating beauty. Unlike the Arecibo message, the Golden Record is not a direct attempt to communicate. The odds of it ever being found by an alien civilization are infinitesimally small. The Voyagers will not pass near another star for 40,000 years. The records are better understood as a memorial, a final whispered testament to our existence sent into the galactic night. They are a message in a bottle, but they are also a mirror. The process of deciding what to include forced us to look at ourselves to ask what is most beautiful, most important, and most worthy of preservation about our noisy, chaotic, and wonderful world. Yet both the Arecibo shout and the Voyager whisper raise the same deeply troubling question. The question at the heart of the METI debate. Is it wise to announce our presence? To its proponents, messaging extraterrestrial intelligence is the logical next step in our cosmic evolution. It is an act of courage and optimism. It assumes that the universe is not a hostile place, and that any civilization advanced enough to receive our message would likely be wise and benevolent. To hide in fear, they argue, is to succumb to paranoia. It is to deny the very spirit of exploration that defines us. Communication, they say, is how knowledge grows. To remain silent is to choose ignorance, to forever sit alone in our corner of the cosmos when we could be joining a grand conversation that may have been going on for eons. It is a gesture of hope, an invitation to a future we can barely imagine. But there is another, much older voice that counsels caution. This is the argument of the precautionary principle, the wisdom that tells you not to call out in a dark forest until you know what else is in there with you. To its advocates, broadcasting our location is an act of unimaginable recklessness. We know nothing of the cosmos beyond our tiny sphere of influence. We do not know if it is empty or populated by benign philosophers or by ruthless colonizers. The range of possible alien motivations is as vast as the universe itself. The late physicist Stephen Hawking was one of the most prominent voices of this concern. He often compared the situation to the first contact between European explorers and the indigenous peoples of the Americas. That encounter, he noted, did not end well for the natives. Why should we assume a cosmic encounter would be any different? An advanced civilization might not be malicious, but simply indifferent. They might view us the way we view bacteria, or as a convenient resource to be exploited. The problem lies in the asymmetry of the risk. If we send a message and are answered by a friendly civilization, the reward is immense knowledge. Friendship, perhaps, a solution to our most intractable problems. But if we send a message and attract the attention of a hostile or indifferent power, the risk is absolute: the subjugation or extinction of our species. The potential gains, however great, may not be worth betting our entire existence. This is not a debate that can be settled with data. It is a philosophical argument, and it cuts to the core of how we see ourselves and our place in the universe. Are we hopeful children reaching out for a parental hand in the dark? Or are we vulnerable prey, foolishly revealing our hiding place? Does our curiosity outweigh our instinct for self-preservation? The Voyager records and the Arecibo message were sent decades ago. They are long gone, racing away from us into the void, carrying their silent data and their hopeful music. The debate about whether we should have sent them and whether we should send more continues. Today, some scientists actively propose beaming powerful, targeted, and information-rich messages toward nearby star systems, arguing that the time for passive listening is over. Others petition for a global moratorium on such transmissions, insisting that a decision of such consequence should not be made by a small group of scientists, but by all of humanity. In the end, this great cosmic choice may not be ours to make. For all our talk of sending messages, for all our arguments about what to say and whether to say it, we have spent nearly a century with our instruments pointed outward, listening. Our dominant posture has been one of quiet, hopeful reception. We have been waiting for the phone to ring. But what if in the midst of our long and patient vigil, our quiet debate about whether to speak is suddenly interrupted by a voice answering back? What happens on the day the silence breaks? Before we venture further into the star-strewn darkness, let us return home, not just to our planet, but to the very idea of life itself. To search for something, we must first have some notion of what it is we are seeking. What is this fragile, tenacious, and impossibly complex phenomenon we call life? What is its essential blueprint? For generations we believed the answer was written here on Earth, and that the cosmic rulebook would read the same everywhere. But our own planet, in its quiet oceans and volcanic vents, has shown us that the rulebook is far more flexible than we ever imagined, and so armed with this humility, we turn our instruments back to the silent heavens. We listen not for a familiar voice, but for any voice at all. For a sign that the great cosmic monologue we have been reciting for millennia is in fact a dialogue waiting to begin. And then one day it happens. It does not arrive with the thunder of a Hollywood blockbuster. There is no grand fleet darkening the skies, no booming voice from the heavens. It arrives as most profound discoveries do, as a whisper, a quiet anomaly on a computer screen in a remote observatory nestled in a silent desert or a lonely mountain range. It is late. The air is still filled only with the low hum of cooling fans and the gentle ticking of atomic clocks. An astronomer weary from a long night of sifting through cosmic static leans closer. There, on a waterfall plot of radio frequencies, is a signal. It is unnaturally narrow, persistent, and orderly. It is a straight line in a universe of curves. It is the kind of signal that nature, in all its chaotic grandeur, does not make. The first emotion is not triumph, but doubt. A profound, rigorous scientific doubt. The human mind is an expert at finding patterns where none exist, at seeing faces in the clouds. And our own technology is noisy. The first suspect is always ourselves. Is it a secret military satellite? A malfunctioning microwave oven in the observatory's kitchen? A stray signal from a passing airplane? This is the first crucial step in what is known as the SETI post-detection protocol. A sober, methodical checklist designed to protect humanity from its own hopeful imagination. The team begins its silent, painstaking work. They repoint the telescope. The signal vanishes. They point it back. The signal returns faint but clear, a persistent pulse from a single fixed point in the sky. It is not from Earth. The first filter has been passed. Now the circle widens. A discrete message is sent to another observatory thousands of miles away. Can you look at these coordinates? At this frequency, see if you find anything unusual. There is no mention of aliens, no breathless speculation, just the cold, calm language of science. Hours turn into a day. The other observatory confirms. They see it too. The signal is real. It is coming from a sun-like star dozens or perhaps hundreds of light years away. The doubt begins to recede, replaced by a feeling that has no adequate name, a mixture of awe, terror, and a sense of profound historical weight. This is the moment that Copernicus, Galileo, and Carl Sagan dreamed of. The moment the human family learns it is no longer alone. The protocol continues. The data is analyzed for any sign of modulation of information. Is it a simple beacon, a lighthouse sweeping through the cosmos? Or is there a message encoded within its rhythm? The verification process could take days, even weeks. Every alternative explanation must be exhausted, every possibility of error ruled out. The small group of scientists who hold this secret carry a burden unlike any other in history. They know that when this news is released, the world they grew up in will cease to exist. A fundamental pillar of human identity, our cosmic solitude, is about to be removed. Finally, when every test has been run and every doubt has been answered, the announcement is made. It is not a panicked press conference. It is a carefully worded statement, likely published in a major scientific journal and presented by the International Astronomical Union. The language is cautious, filled with caveats. A candidate signal of interest. Potentially artificial origin. Further analysis required. But the implication is unmistakable. The silence has been broken. The news ripples across the globe, not as a tidal wave, but as a slow, unstoppable flood. At first, there is disbelief and skepticism. But as the data is shared and confirmed by independent groups worldwide, the reality sinks in. For the first time in our history, all of humanity, 7 billion people divided by nation, by faith, by ideology, shares a single unifying thought: we are not alone. The initial reaction is likely one of profound wonder. The world's great telescopes, both on the ground and in space, would pivot to stare at that single, unassuming star. It would become the most famous point of light in our sky. Children would learn its name in school. It would be a new North Star, a focal point for our collective dreams and fears. But after the initial awe comes the immense, perhaps insurmountable challenge: the message itself. Let us imagine the signal is more than a simple beacon. Let us imagine it carries information. How would we even begin to decipher it? We would have no shared context, no common biology, no Rosetta Stone. An alien intelligence might not perceive the universe through sight or sound. Their mathematics might be based on a different logic. Their message might be encoded in a way our minds are simply not built to comprehend. It would be the ultimate cryptographic puzzle. Linguists, mathematicians, computer scientists, artists, and philosophers from around the world would unite in an unprecedented effort. Perhaps the signal contains what some have called a primer, a self-decoding lesson. It might start with universal constants, the properties of the hydrogen atom, the value of pi. From these shared fundamentals of physics and mathematics, a more complex language could be built, brick by logical brick. Pictures might be encoded in binary pixels, revealing the form of the senders, the shape of their world, the structure of their chemistry. But what if the message is not a scientific treatise? What if it is a work of art, a song, a poem, a philosophical text? How do you translate the concept of love or sorrow into the cold language of mathematics? We might receive the equivalent of the complete works of Shakespeare from another star, and to us, it would be nothing more than meaningless static. We could stare at their greatest masterpiece for 1,000 years and never understand we were looking at art. The greatest discovery in history could be followed by the greatest failure of understanding. And as the long, slow work of deciphering begins, the deeper impacts would take root here on Earth. Our religions, which for millennia have placed humanity at the center of a divine plan, would have to contend with a new reality. For some, it might be a crisis of faith. For others, a profound affirmation, a belief that God's creation is vaster and more wondrous than they had ever imagined. The cosmos would no longer be a backdrop for the human story, but a living stage with other actors. Our philosophies would be reshaped. The existential loneliness that has haunted human thought from its very beginning would be eased, replaced by a new kind of existential humility. We would be forced to see ourselves not as the pinnacle of evolution, but as one branch on a vast cosmic tree of life. Our proudest achievements, our deepest tragedies, our entire history would be seen in a new light as the local story of a single young species in a crowded universe. And what of our politics? For a time, the discovery might bring us together. The old quarrels of nations might seem petty in the face of such a profound revelation. We might finally begin to see ourselves as a single entity Earthlings. But that unity could be fragile. The signal itself could become a source of conflict. Who speaks for Earth? Who decides what we say in reply? A message sent back would be humanity's definitive statement to the cosmos. What would it be? A message of peace, a warning, a plea for help. The debate would rage, and the old lines of power and distrust could easily re-emerge. Then there is the sobering reality of time. The star from which the signal originates is, let's say, 100 light-years away. That means the message we just received left its home world a century ago. The civilization that sent it could be vastly different now. They could be more advanced, or they could be extinct. A reply we send today would not arrive for another 100 years, and their response, if any, would take another century after that to reach us. This is not a conversation. It is an exchange of letters with a 200-year delay between each sentence. It is the slowest dialogue imaginable, a correspondence across an ocean of space-time, so vast that generations are born and die between hello and the hope of a reply. The beings who sent the first message will not be the ones who receive our answer. We are not talking to them. We are talking to their distant descendants. And so, the day the silence breaks is not an end, but a beginning. It is the beginning of a long, slow process of listening, of learning, and of introspection. The discovery of an alien signal would paradoxically be less about them and more about us. It would force us to confront our own nature, our own divisions, and our own place in the universe. The existence of another intelligence would not answer our oldest questions. It would simply force us to ask them with a new and profound urgency. That single faint signal from a distant star would act as a great mirror reflecting our own image back at us across the void. And in that reflection, what would we see? What does this search for another voice truly reveal about the one we all share? Corners reveals life far stranger than we ever imagined. And so, after traveling to the deepest hydrothermal vents and the driest desert sands, after questioning the very blueprint of existence, we find ourselves turning the great lens around one last time. We point it away from the distant star fields and the swirling nebulae and aim it directly back at the source, back at the pale blue dot from which all these questions first arose. For the longest time, we have believed the search for extraterrestrial intelligence was an act of looking out. But perhaps its truest purpose, its most profound revelation, has always been to force us to look in. The greatest discovery of the search for others may in the end be the discovery of ourselves. Imagine for a moment that you are drifting in the absolute stillness between worlds. Your journey has taken you far beyond the familiar orbits of our solar system. Earth is no longer a world of continents and oceans, but a shimmering point of light, a single sapphire pixel against a tapestry of infinite black. From this vantage point, you can see the sun for what it is, not a unique deity of warmth and life, but a rather ordinary middle-aged star, one of billions nestled in the soft, glowing arm of the Milky Way. There is a name for the feeling that washes over those who have seen this sight firsthand. It is called the overview effect. Astronauts speak of it as a cognitive shift, a sudden and profound understanding that changes them forever. From space, the arbitrary lines we draw on maps, the borders that define nations, the walls that separate cultures, they all vanish. They are invisible, imaginary. What remains is a single unified and breathtakingly fragile sphere, wrapped in a whisper-thin veil of atmosphere. It is one system, one home. The search for cosmic company offers us a similar kind of overview, a chance to experience that same shift in perspective without ever leaving the ground. When a radio telescope in California and another in Australia and another in China all coordinate to listen to the same distant star, something remarkable happens. For that moment, humanity acts as a single entity. Our squabbles, our politics, our short-term anxieties, they all become secondary to a shared and noble curiosity. We are not citizens of one nation or another. We are representatives of Earth. We are a planet that is listening. In this collective act, we rehearse a future version of ourselves, a species that has learned to see beyond its divisions, united by a question that is larger than any one of us. The search itself becomes a quiet global ritual of unity, and in that ritual, we hold up a mirror to the stars. Every signal we design to send out into the void is a self-portrait. What do we choose to include? Do we send the equations of physics, the structure of our DNA, the music of Bach? Do we include our philosophies, our art, our histories of conflict and of love? The act of composing such a message forces a difficult and necessary conversation. Who are we? What is the most important thing to know about humanity? To decide what to say to the universe is to decide what matters most to ourselves. The silence that answers us is not empty. It is reflective. It shows us our own hopes, our own values, our own image cast in starlight. As we continue to float in this deep quiet, let your awareness expand, not just in space, but in time. From this cosmic distance, the whole of human history is an impossibly brief flicker. The rise and fall of empires, the birth of religions, the dawn of science, it all unfolds in the blink of a cosmic eye. This perspective brings us to the most sobering and perhaps most important part of our inquiry, a single letter in the famous Drake equation, the letter L. The Drake equation is a beautiful thought experiment, a probabilistic argument that attempts to estimate the number of active communicative civilizations in our galaxy. It multiplies a series of factors: the rate of star formation, the fraction of those stars with planets, the number of those planets that could support life, and so on. Most of the terms in the equation are invitations to cosmic optimism. But the final variable L stands for the length of time for which a civilization releases detectable signals into space. L is not a question about astrophysics or biology. It is a question about sociology, about wisdom, and about survival. A civilization might discover radio astronomy broadcast for a few centuries, and then what they might succumb to self-inflicted disaster, war, environmental collapse, a failure of foresight. Or they might simply lose interest, turning their attention inward. The value of L is the great unknown, the ghost in the machine, and the profound, unnerving silence of the galaxy, the Fermi Paradox, might be its simplest and most terrifying answer. Perhaps L is tragically short. Perhaps the cosmos is filled with the ruins of civilizations that flickered briefly and then extinguished themselves. This thought is not a cause for despair. It is a call to responsibility. The silence of the universe is not an indictment of our loneliness. It is a challenge to our endurance. It compels us to turn our gaze from the stars back to our own world and ask the most critical question of all: how do we increase our own value of L? How do we ensure that the story of humanity does not end after a few short centuries of technology? Suddenly, the search for extraterrestrial intelligence is no longer an abstract academic pursuit. It becomes intimately linked with the most pressing issues of our time: protecting our planet's biosphere, resolving conflicts peacefully, cultivating long-term thinking. These are no longer just good ideas. They are cosmic imperatives. To be a species worthy of contact, we must first become a species worthy of survival. The empty radio channels are a reminder that intelligence alone is not enough. It must be paired with wisdom. The ability to build a radio telescope must be matched by the ability to sustain the world on which it stands. The cosmic silence asks us, will you be the ones to last? Will you be the ones to break the silence, not with a shout, but with the quiet, persistent hum of a civilization that has learned to live in harmony with itself and its home? Let us now begin our gentle return. Let the cosmic vista slowly recede. The galactic arm dissolves back into a field of individual stars. Our sun grows from a bright point into a familiar warming disk. The planets of our solar system swing back into their grand clockwork orbits. And there ahead is the blue and white marble, Earth. As you drift closer, it is no longer just a symbol of unity. It is a world of detail, of complexity, of breathtaking beauty. You see the swirl of clouds, the deep blue of the oceans, the greens and browns of the land. You see the delicate web of city lights on the night side, a testament to the life that huddles there. This is not just a planet, it is our planet. It is the only one we have. The search for a million other worlds in the cosmos only deepens the value of this one. We scan the heavens for a sign of life, all while living on a world that is teeming with it in every drop of water and every handful of soil. The search for cosmic company is, in its final analysis, a profound spiritual exercise. It teaches us humility, reminding us of our infinitesimal place in an immeasurably vast cosmos. It teaches us unity by giving us a common purpose that transcends our petty divisions. It teaches us responsibility by forcing us to confront the fragility of our own existence. And it teaches us hope by encouraging us to believe that we are part of a much grander story, one still waiting to be written. Whether we ever find a signal, whether we are alone or one of many, the search itself will have changed us for the better. We will have looked into the great mirror of the night sky and seen not an alien face, but our own reflected with a new and startling clarity. We will have understood that the journey outward is always and ultimately a journey home, and we will have learned that the silence of the void is not empty. It is full of potential. It is full of the future. It is full of the echo of our own quiet, hopeful, and deeply human question. Closing reflection. And so our journey through the cosmic quiet comes to a close. We began by looking up in wonder, and we end by looking inward with understanding. The search for another voice in the darkness has taught us the value of our own. The silent, star-filled sky is not a void to be feared, but a canvas on which we might paint a better future. It asks of us a simple, profound task: to build a world that is peaceful, to cultivate a wisdom that is deep, and to compose a story that is worthy of being told should anyone anywhere ever be listening. The echoes we seek in the void may simply be the ones we have yet to create.